Scientists thought they understood black holes, and then black holes proved every single assumption wrong. For decades, researchers placed black holes into neat categories: stellar, supermassive, and everything seemed to fit. But the James Webb Space Telescope arrived, and the neat categories began to collapse one by one. Webb revealed supermassive black holes existing only 500 million years after the Big Bang, far too early to exist. The laws of physics said there was not enough time for these giants to have formed, yet there they were. And buried in the data were stranger things still: black holes that broke the speed limit on eating, and tiny ones that refused to die. If black holes breaking every rule has you hooked, subscribe to Noxar Flux right now. We release stories like this every single week. To understand what is happening now, we must go back to the very first second after the Big Bang. Matter was not spread evenly in those earliest moments. Some patches were denser than others, and in the densest patches, something extraordinary was possible. Scientists believe that in the densest pockets of the newborn universe, black holes could form without any star involved. These are called primordial black holes, and they were first predicted all the way back in 1966, though no one had ever proven they existed. But if primordial black holes are real, some of them might be so small they could be circling our galaxy right now without us knowing. Primordial black holes could have formed with masses ranging from asteroid-sized all the way up to hundreds of thousands of times the mass of our Sun. Some could have been no bigger than a single proton but carrying the mass of a full-grown rhinoceros, which is a deeply unsettling thought. The idea was compelling but came with two serious problems, and those problems kept primordial black holes firmly in the realm of theory. If tiny black holes are drifting through our galaxy right now, completely invisible, do you think we will ever find a way to detect them? The first problem was a theory called Hawking radiation, which predicted that black holes slowly evaporate away over vast timescales. According to this idea, all the tiny primordial black holes that formed in the early universe should have completely evaporated by now. If they had all dissolved, they would leave no trace, no evidence, nothing to find, making the entire theory impossible to confirm. The second problem was simpler. No one had ever directly observed a primordial black hole forming. Not from dust, not from gas, only from stars. Then came the James Webb Space Telescope, launched in late 2021. And it began sending back data that no one was fully prepared for. Webb showed us galaxies forming galaxies, and inside those galaxies were supermassive black holes that should not have had time to grow that large. But in July 2025, Webb captured something that changed the conversation entirely: a supermassive black hole sitting between galaxies. Neither of the two galaxies had ejected this black hole. Both still had their own black holes intact at their centers. The team proposed that this third black hole had formed in place from the direct collapse of a gas cloud, with no star involved at all. Then Webb found QS01, a supermassive black hole inside a tiny galaxy with almost no heavy elements present at all. Scientists analyzed the light spectrum and found the galaxy had less than 1% of the oxygen levels seen in our own Milky Way. Stars produce heavy elements in their first generations, and this galaxy had almost none, meaning very few stars had ever formed there. This was compelling evidence that QS01 had not been born from a star at all. It had formed directly from the cosmic matter of the early universe. Neither example was definitive proof, but both added serious weight to the case that the early universe was manufacturing primordial black holes. Now here is where primordial black holes connect to one of the biggest unsolved mysteries in all of science: dark matter. Astronomers tracking gravitational forces in and around galaxies found far more pull than visible matter could account for. What if dark matter is not some exotic unknown particle at all, but simply millions of tiny primordial black holes circling our galaxy right now? Scientists tested this idea by searching for gravitational lensing, the bending of background starlight around an invisible massive object. The search for large primordial black holes circling our galaxy came up empty, no lensing events that matched the expected signature. But tiny primordial black holes are a different matter entirely. Their gravitational footprint would be so small they would be nearly impossible to detect that way. Many scientists believe dark matter forms a massive halo around our galaxy, and tiny primordial black holes would fit perfectly into that halo. If Hawking radiation slows down at tiny scales, as some physicists now believe, those black hole rhinos might still be out there right now. This means that if humanity ever tries to leave the galaxy and reach a neighboring one, we might be flying blind into a minefield of invisible black holes. While primordial black holes raised questions about tiny scales, another discovery was shattering assumptions at the largest scales. A black hole called LID 568 was consuming matter at 40 times the rate that physics said was possible. To understand why that is so remarkable, you need to understand the Eddington limit, the universe's speed limit for how fast a black hole can eat. There is a moment where a black hole can snatch at escaping matter and briefly eat faster than the laws of physics say it should be able to. Stars that push against this limit shed their outer layers through powerful stellar winds. They are already on the verge of destroying themselves. Black holes face the same problem. Their accretion disks glow so brightly that the outward photon pressure starts competing with the inward gravitational pull. This is why simply growing a stellar black hole into a supermassive one over time runs into trouble. Black holes regularly run out of food and have to wait. Adding to the mystery is a suspicious gap in the black hole population. Intermediate mass black holes between stellar and supermassive. If stellar black holes grow into supermassive ones by accumulating mass over time, we should see the intermediate stages, and we do not. LID 568 sits between 12 and 12.3 billion light-years away, so distant that only its infrared emissions are visible. X-ray emissions from LID 568 revealed it was actively consuming matter at a rate that should have been physically impossible by a factor of 40. One possible explanation is jets. When photons are concentrated into a single directional beam, the other directions are free to keep feeding the black hole without resistance. LID 568 might be exploiting a brief window of super Eddington accretion, gorging before the photon feedback finally forces it to stop. If super Eddington accretion is possible even briefly, it changes our understanding of how the first supermassive black holes could have formed so quickly. Computer simulations confirm it is technically possible for a stellar black hole to reach supermassive scale, but it requires feeding near the Eddington limit without pause since birth. Real black holes never get that uninterrupted food supply. They run out of nearby matter, cool down, and wait, which breaks the uninterrupted growth model. This is why the direct collapse theory keeps gaining support. It bypasses the growth problem entirely by creating large black holes without needing a stellar starting point. The orphan black hole web found between two galaxies in 2025 is the strongest direct observational support for the direct collapse theory yet discovered. And then there is LIGO, the Gravitational Wave Observatory, that opened an entirely new way of seeing the universe. When two black holes merge, they release gravitational waves, ripples in the fabric of space-time that travel at the speed of light in all directions. LIGO detected its first gravitational wave signal in 2015, confirming a black hole merger event that had occurred 1.6 billion light-years away. The planned LISA Space Observatory would create a gravitational wave detector spanning 2.5 million kilometers. Microquasars, small black holes inside our own galaxy, are allowing scientists to study quasar mechanics at close range for the first time. The strangest possibility is that every mystery we have discussed tonight, the primordial black holes, the Eddington violations, the most elegant solution is that the universe made large black holes directly in those first chaotic moments, and smaller ones too. This is not yet proven. It is a hypothesis built from converging evidence, but each new Webb finding makes the case a little stronger. For anyone who ever dreamed of humanity leaving the Milky Way, the primordial black hole hypothesis carries a sobering implication. If the galactic halo is filled with primordial black holes we cannot detect, any vessel attempting to cross it would be navigating a minefield it has no instruments to map. A black hole the mass of a rhinoceros compressed to the size of a proton would be invisible, undetectable by radar, and lethal on impact at high speed. The nearest neighboring galaxy to our own is millions of light-years away, and the void between them may not be empty in the way we assumed. Every galaxy we have ever observed appears to sit inside a dark matter halo far larger than the visible galaxy itself. LIGO and the future LISA observatory may finally have the sensitivity to detect gravitational signatures from primordial black hole mergers. LID 568 breaking the Eddington limit proves that our models are not wrong, but they are definitely incomplete, and that is arguably more exciting than being simply wrong. Webb continues to peer deeper into the early universe with every new observing run, and every image adds new constraints to our models of how black holes form and grow. Gravitational wave astronomy has only just begun, and the detections of the next decade will likely rewrite entire chapters of what we know about black hole populations. The galaxy we live in is stranger than we thought a generation ago, and every instrument we build reveals another layer of strangeness. Subscribe to Noxar Flux so you never miss a story. The strange secrets buried inside our galaxy drop here every single week, only on this channel.